these questions. So the things I want to impart with you before the end of the quarter are my own works. First year at DANM, I did a big spreadsheet about different possibilities for interaction between elements. But my favorite part of the whole project was just drawing these cool pictures, which aren't even loading. Luckily, the links are redundant. But for electric systems, you can take use of pretty much all these elements. They instantiate themselves when you're interacting with machines or electrical controls. As for sensors, it gets a little bit into kinematics. There's lots of different switches. One switch that controls parallel lines or routing, so that one thing goes to 12 different places. Most of the switches you see that sell at stores are just trying to get one thing to 2 places, or to 3 places, or 2 things to 2 places. Just real simple little matrices, not too strenuous. You can make a stroke sensor by sewing straight through a fabric with like conductive wire or thread, and then setting up these like hidden contact plates beneath the surface such that there's this offset between the 2 places, the erect and the flat, and then once it's given a stroke, there's all these different threads that some of them are going to make it through and transfer some energy. I think there's some YouTube diagrams of that where it's kind of funny. They just take like a fuzzy shag carpet and inoculate it with electric presence. Flex sensors were made originally it's just like a carbon sheet, and then the more that it's flexed, the closer the molecules are together. So they have like maybe like resistance of 5, but then once they're kind of smushed up against each other, then they have a resistance of 4, and then once they're practically just like stuck next to each other, then they go 3 or 2. But that gives the resistance between 10,000 and maybe like 300, and then computers just decode that, scale it to 0 to 128 probably is how computers talk to each other. Of course, you can put 2 0 to 128s together and get like a 0 to 1,500, no, 15,000, some oddly extreme number. There's pitch sensors on keyboards that have 15,000 states of sensitivity. It seems like overkill. So setting up pressure sensors, oftentimes it's just like making tiramisu, where you are layering either conductivity or routing of electricity that might be conductive. So there's a little bit of difference between doing a binary sensor and a sensor that's for variable resistance. Luckily, there's this IC foam that you can get for just keeping anti-static states for your IC. And for some reason it's conductive, just to make sure all the pins are kind of nulled out, nothing can build up. And that conductivity also is useful just to make a little layer cake, such that when the stuff's squished, then it'll take the copper from the top and transfer the electrons to the copper on the bottom, and vice versa. No picture of the gravity sensor here, but it's just a column with the sensors, steel wires on top and the bottom, and then a loose bearing is controlled by the area's gravity. Base sprockets for those automatically generated pinwheels of copper on a laminate. And just setting up the flicker right here, we'll spin through and you'll get ons and offs and ons and offs and ons and offs. I think I showed you an example of setting up so that you had a giant wheel, and then right at the center you have maybe like a pulse width modulation of kind of like 50-50 ons and offs, and then so there'd be 6. But if you set them up so that they're closer and closer, then ideally, then like one rotation here will give you pulse wave of 6 ons and 6 offs. And then if you set up your numbers right, you also have to account for like getting a bigger circumference of a concentric circle. Then you got like 7 ups, 7 downs, and then 8s and 9s and 10s, so that changing styles from the inside to the outside would hopefully give you practically an analog gradual advancement with how fast you're flickering. So it'd be the same thing as setting up like a timer chip that oscillates based on the resistance of capacitance of a variable sensor, and then just turning a knob on an electric system. Digital electric system. But it's something that we could have done hundreds of thousands of years ago, maybe, compared to 1950s inventing the transistor. But switches are where it's at. I'm all about kind of inventing your own switches, and the first kind of switch that is automated robot switch is a relay, where you set up solenoids and push together 2 pieces of copper. And so you give it a voltage, and then it lets you put together its own voltage. So ideally, you can control a relay with 5 volts or 12 volts, and then it's in its own little vacuum chamber connecting to copper tabs. And those tabs, if they're strong enough, could probably handle 120 volts. You know, they could do AC work for you. So that's usually the big thing is doing step-up empowerment, because 5 volts is where logic is, or control signals. The solenoids aren't exactly logic. You know, sometimes you need 30 volts to throw a solenoid. Relays and solenoids are practically the same thing. The relays just have copper tabs because they're intentionally turned into a switch, whereas solenoids just the switching force of like a nail in a copper winding that's freely able to slide. It's pretty hard to invent a solenoid that can slide more than an inch. Belts, cams, gears, we're talking about them all quarter, hopefully. There's a wide variety of conductive paints and patches. Most recently, I wanted to research and buy some of 3M's electroactive paints, which is the exact same thing as electroluminescent wire, where a coating of phosphor is around kind of like a steel mandrel, and on top of that, there's these 2 threads of the opposite electric polarity. So it's kind of like a corn dog wrapped in the ketchup or something. And the ketchup is negative, and then the dog itself is positive, and then the phosphor is like, whoa, I'm getting positive on one side and negative on the other. I might as well just turn on. So it gets it's great. They could put a little pigment in the electroluminescent particle. It's like a powder that they anneal to the surface. But conductive paints, I've heard that you can make solar panels out of making kind of like an ionized vacuum zone that's just like a screen printed heat sink of nickel. And then maybe it's got some kind of ionized embedded trough and it's covered with glass. And maybe it's a little bit of a greenhouse because it heats up inside of that vacuum space. but if it really is a vacuum, I don't know. Molecules can travel through it. But nickel, it can be turned into a substrate that's used as paint. A lot of paints are water-based. In screen printing, you might get something like plastisol that's just like this goo, and it doesn't dry by itself. So on the one hand, it's a great material to work with, because you don't have to hurry. You're not water-based. You're not evaporating. It's just going to be goo forever. But then you realize, well, if my shirt doesn't cure in the oven just right, then it's going to be goo forever on a t-shirt, and that's kind of an icky predicament. So yeah, water-based paints are usually safer. But how would you suspend metal in water? You know, iron's just going to rust. They sell little paint pens for overpriced amounts, but you probably won't end up buying something that wasn't referred to as a technical material. You know, you just buy the nickel powder, or they sell silver paint. Usually, I think the newest thing is that they're just trying to do carbon paint. You can buy these little circuit tracer paint pens that'll fix up a broken machine for you. But of course, the opposite of painting is etching. Instead of adding, you just take away. So when people see a circuit board, they usually wonder how you tell someone painted with copper, and the answer is they just painted with what wasn't copper. This stuff, the Velostat plastic's pretty cool material. It's just a black sheeting you can get through 3M. You have to use that word Velostat to find it. Some people that used to be in the military, they used it to make stop alien mind control helmets. If you just put like 8 layers of this material on your head, then it just makes a null state where radio frequencies can't emit. But strangely enough, aside from being good for that, it's also a flex sensor. There's this really cool kind of homebrew method of making a flex sensor out of it, where you sew a piece of copper through a substrate like this, and then the back looks like that. So you want these diagonals, and then you sew it in the exact opposite direction, or something. It's kind of weird. Like you're gonna take one and sandwich it with the other one, and the other one you're gonna want it to look like you're gonna want it to look the same, which means you had to make it different. So this material right here has 2 rows of copper, which are close to each other in proximity, and then the Velostat has enough electronic availability that whatever's on this one can just kind of sneak warily across to this one. So they bridge a gap. From the side view, you have 1, and then you have 2, and then in between it, you just have this sheet of Velostat. So it's usually sometimes just 3 layers about that then. With this configuration, and then you can clench it just like the original flex sensor, which are made in the industry to do carbon. The Velostat's not carbon, it's suspended in plastic as well. But the principle of setting up kind of like close to almost touching, that's been around for, you know, since computers, since calculators been around. Because the whole concept of heat sinks comes back. You know, if you have a bright, powerful heat and you want to dissipate it, ideally you just set up all these metal surface areas so that air can get in and heat can get out. So there's got to be lots of surface area. Same thing is true, exact same thing works to make a button system. You just set up 2 F's, negative and positive, something goes in and then has this many chances to get out if a big fat thumb presses this area, so like a piece of carbon takes stuff from the left and pushes it to the right. But everything from a nail to a brass brad, most metals are conductive. I think it might even be a property that metal has to have. It'd be fun to find a non-conductive metal. Couldn't weld it. But you find copper pins in old machines and organs. Everything from a spring to metal fasteners. Calder and Forrest Mims, some of their first hobby toys when they were young, when they first did their electronic experiments, were just a thumbtack and paper clip. But Calder decided not to get back into electricity because he started a pretty bad spark by making a really, really low quality switch out of some scraps. So these, aside from materials you work with, like the paints in your artist box, there's also principles, or like what can be accomplished with these different themed work. So welding, soldering, screen printing, I think that says music, and tempering, doing LFO work with analog copper. Kinetic relocation is just saying, like, if you just set up a big spaghetti of wires, like you can take something from one place and send it to any other place. And that way you can do like micro to macro work where you touch like a 2x2 pad of 1,000 sensors, and then that effectual electronic movement can go out to something that's 1,000 feet long. You can control the Bay Bridge with a little comm panel. And it wouldn't even have to be digital, it could just be 1,000 wires next to each other. And yeah, Florida post transference is just, again, setting up these little experiments like layer cakes. If the power's on the bottom, insulation's in the middle, ground's on the top, and then there's LEDs that are allowed to kind of wiggle between those layers. In this particular model, I think I made welded a bunch of nails to this sheet metal. And then push down on top of it a layer of foam for insulation. And then that would poke through all the nails, and the nails are still on top. And then above that, you just put down pieces of aluminum foil and make sure it's kind of opened up so it's not touching the nails. So then you got foil here, and underneath the whole thing you've got insulated metal. And all you have to do is let loose a billiard ball or a steel marble, and it's just kind of like analog pachinko. Once the steel marble touches one of these posts, it transfers the energy from the ground to the post, and then there's this LED hanging out on the top of the post. So it just automatically goes off. So you can have 1,000 steel balls in these little pinball games, and each one of them acts as its own kind of like polyphonic light generator. Because you can make systems that aren't dependent on one interaction, they're just dependent on any interaction. There's a couple projects that went straight to what was accomplished through music. If you use piezo speakers, they're going to give you a voltage between like 0 and 1 volts. It's really infinitesimally fast when it hears something. Piezos are kind of like microphones for physical vibration rather than acoustic air vibration. But luckily, when a guitar makes sound, it's doing both. It's if a piezo is glued to it and a microphone's beside it, they're going to get two different flavors of the same resonance. I don't know if it's worth getting into machining too far, because pretty much every machine that's deemed so, you can't use it while you're feeling emotionally distraught or drinking. It's like art that you have to only do seriously. And I don't know. It's hard to really want machines that could kill you in your comfortable home. So yeah, don't get a drill, or if you get a drill press, don't leave the chuck in it, because that's playing roulette with your life. programming always comes back to it, because luckily you can create something in the real world that inspires you to create something in the digital world, and then you can create something in the digital world that says, in terms of the real world, to make a new improvement. And so they kind of double back and feed upon each other's possibilities. So it's good to get in the, I don't know, kind of like the harvest feedback loop between software and sculpture. I think I showed you that one audio spatialization piece. I mentioned Verez's work in spatialization. But, you know, sound might travel like 300 or 600 miles per hour, but electricity travels at like 80% the speed of light. So you can set up speakers that are far away from each other, and then you can send the same, like send sounds to them faster than the sounds could get there through the air. So there's just like a kinetic sculpture for you know, like Calder's mobiles is something that you really have to appreciate in 3D space. So there's a whole genre of audio works that are, you know, their sound art, their audio sculpture that require 3D space to understand that the ear is everywhere, and everywhere the ear is, there's a different thing to hear, especially in a time-based art. But when you put on headphones, you're hearing wherever something was recorded, be it digitally or acoustically. You're just hearing a particular space, and you know that space is really kind of chosen for you. They have some emulation software. You might have seen it where in virtual space you can say where the speaker is, and you can say like where you as a listener are sitting. So you get like this virtual picture box that has two speakers and like you in a certain 2D rotation. And you can just grab yourself, move yourself over here, and then it'll do the computations to say right speaker gets to you in like 0.3 seconds, left speaker gets to you in like 0.5 seconds, and then you get you know, a different concept of the phase. But if you have a nice soundproof room and you just walk around it, you're going to hear like binaural beats, you're going to hear transitions between what the sound is. Because this is we saw that cool light slowing down MIT project. Yeah, we can do that inherently with sound without any expensive trillion frames per second system. And right down there at the bottom is like 30 different electronic artworks that I have done. Some are just kinetic works. Give it a click, read about them, ask me about them. Probably the coolest one that I just got into. For a while I didn't really like electronics per se, you know, didn't want to just repeat circuits and wonder why they didn't work. Just wanted to start from the ground up, you know, black and white. And aside from just kind of diodes that make light, there's just regular diodes that do what diodes do, which is block energy. So energy only goes one way through a diode. So if you think about it, I heard that it's possible to make like an OR gate just using diodes. I don't have the schematic in front of me. But one thing that you can do really easily is set up arrays of lights, and then have like a bunch of different buttons, and each button goes to say a different, or goes to diodes that go to different ones of those lights. So say you have 10 buttons, each one goes to 200 of 400 lights. And that way you can sculpt, with diodes, you can sculpt you know, like the control array for 10 different pictures that all share the same light field. And of course you can turn on, you know, a couple at the same time, and they'll just intersect. Possibly, no, they'll probably just give the same light to everyone. I was thinking that if they got electricity from 2 different diodes, that they might be a little brighter, but I doubt it. Electricity is electricity. So there's also one page I didn't bother to put on the syllabus because it's a little bit different genre of work. Can't even spell it right. EA. Luckily the picture's working better on this side. I'll leave it up to you if you want to save this URL so you can check it out. But this was the study. Like I did the Electromancy study the first year in DANM, and the second year I did this one, which is like video games dismantled. You know, like Electromancy is a lot based on dismantling the physical world. But luckily, there's also a virtual world that needs to be, you know, put back to rest. So what this is all about is, it's mostly about Nintendo. One of the first visual feedback systems, you know, it's kind of cybernetic. If you think about it, all of your save games inside of a Nintendo game are read-only memory, you know? Like you play Mega Man, the first time you play it, you press in a password and you can go instantly to level 7. And you think about the teleology of it, like this game, you've never been to level 1, but you can get to level 7, it's kind of hard to believe. So the worlds are already there, but they're early worlds that were kind of flawed. These video games had lots of limits for what they could accomplish, and luckily they had to do a lot of shortcuts. And when you do a shortcut, you're sacrificing what you know should be the long and methodical way just to get by, just to say, well, I only have 12K memory, and I have to convince people that there's something happening. So it's fun to, a lot of people have abused these early video games to find out what's still a possible world state. So I'll just click on illusions maybe. But there's some interesting content here about linear feedback arrays and shift registers. Some fun programming concepts that come up in game design and in generating random numbers inside of a kind of a closed world. A lot of video games they just seed their random number generator based on when you press the start button at the beginning of the game. So they're kind of closed random systems. Here's all 16 of the possible logic gates. We only concern ourselves with like less than half of them because the other ones are almost illogical. But these cool modules called linear shift registers, and what they do is they just say, I'm going to compute my state once every turn, and my state is based on this logic gate. So here I think it's an OR gate, and then the last two are outputting to be the input for the next state in the logic gate. And this is a slightly famous one, as famous as a logic gate can be. I think this is, I don't know why, I think it's Fibonacci. Oh, here's the Fibonacci one. But before that, it's just one diode. And it goes through all, say 16 permutations of possibilities, and then before repeating itself. And I think they'd always repeat themselves, they're methodical, logical process. But if you think about like pi, you could say that pi is like a methodical, logical system, but it's just one that never needs to repeat itself. Let's hope. So this one, Fibonacci's 16-step linear feedback register, or LSFR or something. Stuff like this is used to invent random numbers in your video games. Just take 16 bits of memory, and do this little computation to them, and you're going to get a new state that's idiosyncratic. It wouldn't come to mind from any thought. The enemy's going to jump in a new direction, kind of stuff. These little programs were invented by I think his first name was John Van Neumann. He's a kind of at least percentage,ally involved in inventing a nuclear bomb in a Manhattan project, but he also did a completely different body of works in cellular automata. So he invented them on paper, which is like a lot of how a lot of computer programs were invented in the 50s. And say Conway's Game of Life, might have been in the 70s when he actually had a little PC to put it together on the screen, do the renders to find kind of like the automatic creativity in it. But what Van Neumann was after back in the 50s with these was he needed a new way to generate random numbers, because what they were doing for the longest time was doing automatic entries of pieces of paper that were like statistical mapouts. If you ever take a statistics class, there's this hilarious page on the back of the book that's called Random Numbers, and you're supposed to just take them and knock them off as if that was random. But as random as it might be, to use a really powerful equation to invent like 100,000 random numbers and then just go by those. He generated them on the fly, and he said that was like 200 times faster to have a little rickety computer program generate his random numbers than to have to do a manual feed of the next seed. So these are pretty linear, and then this one's a little less linear because you're taking input points at different places. It's differently stacked. But you can think, as soon as you've seen these three examples, you can think that there's 1,000 other possible ones that are just going to create these sequences on drops. And they're using feedback. The system is self-attenuating. And like a video game like this is where you're going to see these little check loops working. It's like, what is this animal going to do next? Is he going to put his shield up, left, right? And then you have to supposedly battle a visualization of a little logic block. So back to this one, today's page. These are the two pages, or the two papers I did for DANM. This is the thesis page. It's called This Interaction, Machines and Cyberprimitivist Music. It's like 50 pages. It's got like, it's 50 megabytes, it's got 50 pictures. It's pretty good if you wanted to check it out. And then this earlier one, Automism and Automata. If you remember, we've been talking a bit about automata, machines that do things automatically, and usually anthropocentrically. This paper is about the different parallels we have in like surrealist art, and how maybe in the 70s and 60s, 50s, surrealism, World War II, Andre Breton was inventing tricks like exquisite corpse, and got us for creating cut-ups on their poetry. A lot like the linear feedback shift registers, where they're inventing ways to do functions on their art so that they can output new art or generate permutations of art. So even just biomorphic drawing, which is a form of psychic automism, which is basically just putting your pen to paper and just drawing what has to be drawn. It's almost like it invents itself. Andre Breton was a poet who mentioned the form using language, where you just write stream of consciousness on paper, and anytime you ever get stuck, for him, his key calling was to say, we'll go back to the letter L. Start with a word that starts with the letter L, and then keep going. What do you do when you're stumped? You stop, and then maybe you wait until something else happens. When I was in a free write class in English undergrad work, the teacher would say, this is the free write time. Whenever you get stuck, just write that same exact word that you were stuck on until it grows into something that transcends the monotony. Yeah, so the DANM program, really you only had to write 2 papers for it. I think this one's like 20 pages and the final one's like 40. I do take some time in this particular Automism Automata paper to talk about Peter Elsey's fuzzy logic, as well as genetic algorithms, and a little bit about neural nets, which is always a topic that, like how much can you know about it? because they inherently in themselves are black boxes. They are letting the computer just kind of like bacteria fester, and then you just do generations of them until they get better at these kind of like achievements that you set for them. And like personally, I can never really understand why to use them or how to use them, because if you know what the achievements are, you're pretty much done. You know what the program should do. But these guys are starting from the ground up. The programmers are like GAs, genetic algorithms, and or neural nets. They're just looking for kind of like a population or a diversity of solutions to problems instead of just the full completist answer. And I don't know, it seems a little scary, almost like offering up your autonomy to the computer and just saying, computer, find out the answer for me. I don't even care how you do it. So I think I brought up a page that was the particular guys that were doing the genetic algorithms, or no, the neural nets. Neural nets, soccer. We can just watch this all day, but just check this out. Like, you can't understand that. This guy's got 16 inputs. It says right here, like north, south, east, west. Like, who are your friends? Who are your four closest friends? Who are your four closest opponents? Something about like which distance is the ball. So if it was in northeast, then those two get like 0.5, and then southwest we get like negative 0.5. And distance to field borders. And there's all this hidden permutation because you want to output 4 concepts. Direction, power, do I dash or not, or do I turn or not? And so you've probably seen it in stuff like the Blades, which is kind of like a famous program that emulates schools. Fish and birds travel in schools where it just seems like they have an overarching truth to like what they're trying to do, when in fact like they're all just autonomous individuals that seem to accomplish like a mass hive mind. So if you wanted to make a soccer program, you wouldn't really like this guy's after making a program that he's going to be kind of like enchanted by. He doesn't want to make the perfect program. He just wants to create possibilities in play. So it's really like like the observer in art, rather than deciding what it is. It's just deciding that it should start trying to play.
Red is going on, and goal! They did it.
So check out their website if you want a little bit more information about that. Just go to Google and just look at neural nets. It'll take a while to realize what in the world they're doing. And supposedly they're called neural nets because they're modeled after our axons, modeled after how we ourselves think. It's hard to believe, but I think we have a couple million of these neural nets, or these axons with their neuron centers, and that they all have these little tentacle whips to each other that invent their state. And their state usually is just like if I'm going to send out a new action impulse or not. So it's all these analog control, or binary kind of. Either the axion says yes or no. So next time you think you create a project or a problem that's a little bit too complicated for yourself, then that might be the point at which you just want to generate thousands of solutions to the problem, and then just observe which one seems to be the most appropriate. And then someone would ask you how you came to that conclusion, and you just say, well, I just observed permutation. Okay, last little bit about cybernetics. Norbert Weiner is the guy that invented it. He was helping out during World War II trying to invent better weapons. Intelligent killing machines, like how are you going to shoot at a plane that's moving? What if the machine gun could almost taste the moving plane? But cybernetic systems in their primitive state have existed since the 17th century, and by primitive I just mean almost like the escapement device on clocks. There's this other device called like the bell. I don't think the picture's loaded. Where are the pictures? I have to reset. It's kind of related to the flywheel, but there's this kind of elevator, they call them the governors, and it's just like this flywheel thing that elevates the faster that the engine goes, and then if it elevates to a certain threshold, then it sends a lever to, again, close the motor. So it's the first self-regulating system to be invented, and they were used on windmills and grinders, grinding stones in the 17th century. And then Watt invented it for the steam engine. He didn't claim he invented it, but shoot, it was the first one made out of steel, running at high RPMs. And then that mechanical inspiration kind of brought us into what cybernetics did to make smart machines after the 50s. And the first example of a smart machine is just kind of like guns that don't lock up. I think they just wanted a gun that didn't lock up in the snow. It would have like some kind of thermal sensor, and when it got to a certain point, then it would just change how it dealt with firing, because a certain type of firing just couldn't happen in the cold. Everyone has a toaster or a CD player, just wants to push it closed after they're done with it. But sometimes, like early ones, they had a button that said, like, this is the push close button. And I think there's certain toasters these days that you can accidentally damage if you open them, and that they have a button, like you're supposed to press this button to make it, auto eject. But even the way that sticky notes are accordion tiled, it's almost a little bit like a feedback regulator. Oops. So here's what a flywheel is. It's kind of related to the governor. It's a pretty cool concept that with a flywheel you can put things in an inertia that's higher than any inertia that you could have attained. So you can make motors that can say get something up to like a speed of 5, but if you use them to power a flywheel, then you can get the flywheel up to like a speed of 10, and then you can use all that power instantaneously. It kind of reminds me of how they say that we make, you can't even see this thing. It reminds me of how they say that, you can use machines to make sharper machines. Use machines that can handle like the millimeter to create a machine that handles the micrometer. So here's Norbert hanging out with one of his first feedback regulating machines. His first book was just kind of like Cybernetics and about control, and the second book wasn't just about computers anymore. He said, we're going out to the mainstream. So it was about human use of human beings. So he was branching out Cybernetics to be just about machines, to be about physiological processes. And then from there, it just took over. And these days, Cybernetics has kind of embedded itself in management, like business management, and quite well anywhere. It can be kind of like a new kind of philosophy. So here's the flyball governor. You can see that these two nodules will start to levitate if the the fulcrum's going fast, and then it'll pull on this lever that throttles the motor. This particular character, he's an embroiderer. He uses machines to embroider, and he particularly likes glitch embroidery, which I thought was an interesting kind of cybernetic art. It's to have a machine make something, and then you only want what it messed up doing. Because in a way, yeah, like creative honor thy error form, this is an example of a creative machine. Because it wasn't told to do this, but it did. And luckily there's this whole website about the new rage of 3D printers, the little ones the cheesy ones that shoot out plastic goop. There's a whole website devoted to showing you how horribly they've damaged intentional sculptures by just being offset with their registers. So I've got this cool 50-minute video from Melbourne about cybernetics, and I think that'd be a good drone for the background while you guys are just hopefully just going through the test. I renamed them all like 1 through 50 and gave them all numbers, and all I'm expecting from you is tell me what it is or what it's for. In some examples there's like laser cuts, designs of objects. Other examples there's it could just be conceptual, it could be physical, but pretty much everyone is either a 1 or 2 word answer or a less than 1 sentence answer. And don't worry about names so much as principles or meaning. And there's 2 answers in here that you can use twice, according to how I went about it. And if you give each one a minute, then we're out of here by 1. And you can just send me an email with list 1 through 50, and then that'll do it.